1 million lines of production code by an AI agent, 0 lines written by a human engineer. This is not a research demo. This is not a benchmark. This happened in a real software repository, and it happened because the team stopped thinking about prompts and started thinking about harnesses. Here is the critical insight that most engineers miss. The OpenAI Codex autonomous agent did not succeed because someone wrote a better prompt. It succeeded because the entire operational environment, the rules, the constraints, the feedback loops, the file structures, was engineered as a system. The prompt was the smallest variable in the equation. If your mental model of AI engineering still starts and ends with a prompt, you are optimizing the wrong layer. By the end of this lecture, you will have a complete architectural framework to operate at the layer that actually controls outcomes. Let us be precise about what this incident reveals structurally. For the past 3 years, the industry trained engineers to believe that model capability was the ceiling. If the AI failed, you wrote a better prompt. If the output was wrong, you added more context to the prompt. This mental model made sense when AI was a single-shot text generator. But autonomous agents are not text generators. They are stateful, multi-step execution systems operating across tool calls, file systems, APIs, and external state. And here is the structural mismatch. Prompt engineering operates at the utterance level. Agent-controlled design operates at the system level. When you send an agent to complete a 1,000-step task, the prompt is gone by step 3. What governs the remaining 997 steps? That is the control gap. That gap is now the most expensive engineering problem in the industry, and most teams do not even have a name for it yet. But wait, if this gap is so critical, why did it take until 2026 for the industry to converge on a solution? Now here is what makes April 2026 a genuine inflection point, not just another AI hype cycle peak. In the same 30 window, 3 independent organizations published foundational documentation on what they all called, in different words, the same thing. Martin Fowler published his essay on AI-assisted development harnesses on martinfowler.com. OpenAI released the AGENTS.md specification framework for autonomous agent configuration, and Red Hat published its enterprise AI governance architecture, explicitly naming harness engineering as a first-class discipline. 3 organizations. 3 independent research tracks, 1 month, 1 converge and conclusion. In the history of software engineering, this pattern, independent simultaneous convergence, is how paradigm shifts get ratified. It happened with REST in 2000. It happened with DevOps in 2009, and it is happening now with harness engineering. The question is not whether this transition is real. The question is how fast your organization will position itself on the right side of it. In the next section, I will show you exactly what you will be able to design and build by the end of this lecture. Let me be direct about what this lecture delivers. Because your time has a cost, and you deserve a precise return on investment statement before we go deeper. By the time you finish all 6 chapters, you will have 5 concrete engineering capabilities. First, you will be able to classify any AI engineering practice into one of 3 generations: prompt engineering, context engineering, or harness engineering, and articulate exactly why each generation's ceiling exists. This classification framework alone will restructure how your team evaluates AI tooling. Second, you will be able to write a production-grade CLAUDE.md harness specification file, the document that governs how Claude code operates inside your codebase at the system level. Third, you will be able to write an AGENTS.md file, the OpenAI standard agent configuration that defines tool permissions, escalation rules, and behavioral boundaries for autonomous agents. Fourth, you will be able to architect a multi-agent control system using formal IT strategy frameworks, not intuition, not trial and error, but a repeatable design methodology. And fifth, you will understand why every senior engineer, tech lead, and solution architect who does not make this transition in the next 12 months will be operating with a systematically outdated mental model. These are not soft skills. These are structural design competencies. The next chapter maps the exact evolutionary path that brought us here, and why understanding that path is not optional if you want to design systems that scale. Let us build the taxonomy. Let's establish a precise definition before we go any further. Prompt engineering is the discipline of crafting input text, the prompt, to steer the output of a large language model within a single interaction session. That's the operative word, single. You write a prompt, the model responds, and the transaction is complete. The 3 canonical techniques are zero-shot, where you provide no examples and rely purely on instruction; few-shot, where you embed 2 to 5 worked examples directly inside the prompt to guide output format; and chain of thought, where you explicitly instruct the model to reason step by step before answering. These are elegant techniques. They genuinely work. Between 2020 and 2022, mastering these 3 patterns was a competitive advantage. But here is the critical architectural constraint you must internalize right now. Every single one of these techniques operates entirely within the boundary of one model call. One prompt in, one completion out. The intelligence lives inside the model. The engineer's job is simply to phrase the question better. And that, as we're about to see, is exactly where the ceiling is. The next scene will show you what happens when that ceiling is hit in a real production system. Now let's look at what happens when prompt engineering meets a real enterprise task. Imagine you need an AI system to autonomous audit a codebase of 50,000 lines, identify security vulnerabilities, cross-reference them against the NIST AS to 53.3 control catalog, and generate remediation tickets. A prompt engineer's instinct is to write a better prompt. But the architectural reality is brutal. The context window fills up after roughly 8,000 to 32,000 tokens, depending on your model vintage. The model is stateless. It has no memory of step 1 when it reaches step 4. And crucially, there is no mechanism to say if this tool call fails, retry with a different strategy. The before state is a developer endlessly iterating prompt wording, getting inconsistent outputs, hitting token limits mid-task, and manually stitching results together. The after state, spoiler alert, is not a better prompt. It's a completely different abstraction. Statelessness is not a bug that better prompt writing fixes. It is a fundamental architectural property of Generation 1 systems. The context window is not a storage system. It is a one-time consumption of available attention. This is the structural ceiling, and recognizing it is the first step to understanding why the industry had to evolve. But the question is, what did the industry reach for first? Not engineering. Not yet. To understand why Generation 1 was even celebrated, we need the historical context. GPT-3 was released in June 2020, and the world was genuinely stunned. For the first time, a language model could follow complex natural language instructions without any fine-tuning. By 2021, the term prompt engineering appeared in job postings. By early 2022, practitioners were publishing prompt pattern libraries. DARE released the prompt engineering guide, and companies were paying specialists $100,000 a year for this skill. This was rational. At the time, it was the most powerful lever available. But by mid-2022, two things happened simultaneously. GPT-3.5 and the earliest ChatGPT experiments began exposing the context ceiling in real workflows, and the first papers on retrieval augmented generation, RAG, started circulating. The cracks were showing. Prompt engineering was not wrong. It was a necessary first-generation response to a new paradigm. But the industry was already asking the next question. What if the problem isn't how we phrase the question? What information we give the model to work with? That question launched Generation 2. And the tooling ecosystem followed changed everything. Briefly, Generation 2 is defined by a critical reframe. The problem is not how you phrase the question. The problem is what information the model has access to when it answers. Context engineering is the systematic discipline of designing, managing, and dynamically populating the context window with precisely the right information at precisely the right moment. This is architecturally deeper than prompt engineering. The primary artifact is no longer a text string, it's a pipeline. The canonical pattern here is retrieval augmented generation, RAG, first formalized in the Lewis et al. Paper at NeurIPS 2020, but industrialized at scale from 2022 onward. In a RAG pipeline, documents are chunked, embedded into a vector space, stored in a vector database such as Pinecone or Weaviate, and then at inference time, semantically similar chunks are retrieved and injected into the context window alongside the query. Beyond RAG, Generation 2 introduced episodic memory stores, conversation summary buffers, and long context models with 128 token windows from Anthropic and Google. The mental model shift is profound. The engineer is no longer writing a better question. The engineer is curating the informational environment in which the model operates. This is a genuine abstraction level up. But it still has a ceiling. And that ceiling is about to matter enormously. Here is where Generation 2 hits its own wall, and it's a different wall at a higher elevation, but it's still a wall. Consider a multi-agent system where one agent is responsible for code generation, a second for testing, and a third for deployment validation. Even if every single agent has a perfectly engineered context window, the right documents, the right memory, the right retrieval, context engineering has nothing to say about what happens when the code generation agent produces something the testing agent cannot parse. It has no mechanism for the testing agent to signal failure back to the code generation agent and trigger a revised attempt. It cannot manage the sequencing of tool calls across agents. It cannot enforce that the deployment agent only runs after the testing agent returns a passing status. These are orchestration problems, not information problems. They require a control layer that sits above the individual model call. And this is the precise point where the industry realized that RAG pipelines and long context models were solving the wrong layer of the problem for autonomous systems. You cannot retrieve your way out of a coordination failure. So what does the next generation look like? It looks like engineering the environment itself. The 2022 to 2024 period was the Generation 2 gold rush. LangChain launched in October 2022 and reached 60,000 GitHub stars within 6 months, the fastest AI framework in history at that point. Llama Index followed as a specialized context management layer. Pinecone, Weaviate, and Chroma emerged as a new infrastructure category, the vector database market, projected by Markets and Markets to reach the law some billion by 2020. Context-related. GPT-4's 8K window became 28K with GPT-4 Turbo in late 2023. Anthropic's Claude 2 shipped with 100K tokens. Google's Gemini 1.5 Pro reached 1 million tokens in early 2024. The industry ran hard in this direction, but by late 2024, a pattern became visible. Companies that had deployed sophisticated RAG pipelines were still reporting 40 to 60% failure rates on complex multi-step tasks, according to Stanford AI benchmarks. The retrieval was working. The coordination was failing. And that gap between perfect information and reliable autonomous action is exactly where harness engineering steps in. The third generation is not an incremental improvement, it is a category change. Now we arrive at the third generation. Harness engineering is the discipline of designing the environment, constraints, tooling, and behavioral specifications that govern autonomous agent execution. Let me be precise about what this means, because 3 major authorities converged on this definition simultaneously, which itself is a signal worth noting. Martin Fowler at ThoughtWorks defines a harness as the surrounding infrastructure that makes agents safe to deploy. The guardrails, the observability hooks, the rollback mechanisms. OpenAI's platform documentation from their Agents SDK describes the harness as the specification of agent roles, tool permissions, and handoff protocols. Red Hat's Enterprise AI Architecture Guide frames it as the control plane that sits above the model and the context, managing lifecycle, policy enforcement, and audit trails. What is common across all 3? The locus of control has moved. In Generation 1, control lived in the text of the prompt. In Generation 2, control lived in the content of the context window. In Generation 3, control lives in the structural environment the agent operates inside, the AGENTS.md specification file, the tool permission manifest, the task graph, the constraint architecture. The model is no longer the system. The model is a component inside the system. And that inversion changes everything, how we design, test, and govern AI in production. But what does this harness actually look like in practice? That is exactly what the next chapter will build for you from the ground up. To make the 3 generations concrete and comparable, let's put them side by side across 6 dimensions that matter for engineering practice. First, locus of control. In Generation 1, it's inside the text, you control by phrasing. In Generation 2, it's inside the context window, you control by what information you inject. In Generation 3, it's inside the system environment. You control by what the agent is structurally permitted and required to do. Second, state management. Generation 1 is stateless by design. Generation 2 has managed context state, memory stores, retrieval indexes. Generation 3 has pristine agent state, task graphs, long-running execution traces. Third primary artifact. Generation 1 produces a prompt string. Generation 2 produces a retrieval pipeline configuration. Generation 3 produces a harness specification, the AGENTS.md, the tool manifest, the control graph. Fourth, failure mode. Generation 1 fails silently with hallucination. Generation 2 fails with retrieval noise or context poisoning. Generation 3 fails with constraint violations or agent deadlock. And crucially, these failures are detectable and recoverable by design. Fifth, human intervention point. Generation 1 requires human review of every output. Generation 2 requires human curation of retrieval sources. Generation 3 defines human checkpoints as first-class architectural components. And sixth, acquired skill. 1 needs a skilled writer. Generation 2 needs a data engineer. Generation 3 needs a systems architect. The progression is not accidental. It mirrors exactly how software engineering matured from scripting to programming to architecture. Let's synthesize everything from this chapter into a single mental model you can use as a diagnostic tool. Every generation of AI engineering is defined by where control lives. Generation 1 encodes control in tokens, in the specific words you choose. When you need more control, you write more words. Generation 2 encodes control in context, in the information you select and retrieve. When you need more control, you engineer better retrieval. Generation 3 encodes control in the system environment, in the harness. When you need more control, you design better constraints, better specifications, better agent boundaries. The 2025 inflection point is not a matter of debate. By April 2025, Martin Fowler, OpenAI's platform team, and Red Hat's AI architecture division had all independently published documentation using the term harness as the dominant architectural metaphor for production AI systems. That simultaneous convergence from a researcher, a platform vendor, and an enterprise middleware company is the industry signal that a generational shift has crystallized. The taxonomy is now settled. Prompt engineering is a tool. Context engineering is an infrastructure pattern. Harness engineering is an architectural discipline. And architectural disciplines, as information management professionals know from TAF, ETIL, and ISO 42 ETS, define the practice for the next decade. In Chapter 3, we will open the harness itself and show you exactly what its core mechanisms look like, component by component. The internal architecture of a harness is where the real engineering decisions are made. And it is more precise and more teachable than anything we have seen in the previous 2 generations. Let's build the harness from the ground up. A harness is not a single file or a clever prompt. It is a 5-layer architectural stack. At the top sits the behavioral specifying layer. This is where you declare what the agent is, not just what it should do in one session. Below that is the tool and capability manifest, the explicit registry of every external action the agent is permitted to invoke. The third layer is the environment constraint boundary, which defines the operational sandbox. File paths, AIs, and system resources are in scope. Fourth is agent topology configuration, how agents relate to each other in multi-agent deployments, who orchestrates whom. At the base sits the observability and override interface, the control plane that lets humans inspect, interrupt, and correct agent behavior in production. 5 layers. Each one maps directly to a classical information systems architecture concern. But here is the critical insight most engineers miss. If any single layer is absent, the entire harness degrades to an expensive prompt wrapper. Which layer do organizations almost always skip first? We will. Right now. The most tangible artifact of the harness is a file. Specifically, 2 files, CLAUDE.md and AGENTS.md. When Claude Code reads a CLAUDE.md in your project root, it does not treat that file as a suggestion. It treats it as a behavioral contract that persists across every session, every task, every agent invocation in that project. This is architecturally profound. Think about the difference between a verbal instruction you give a contractor once versus a signed scope of work document that governs every decision for the duration of the engagement. CLAUDE.md is the scope of work. AGENTS.md extends this multi-agent scenarios, assigning roles and boundaries to each participating agent. These are not configuration files in the traditional DevOps sense. They are specification artifacts. They belong in your version control system. They should be code reviewed. They should have changed history. Martin Fowler's team at ThoughtWorks, OpenAI's deployment guidelines, and Red Hat's enterprise AI frameworks all converge on this same principle. The specification artifact is the primary engineering deliverable of the harness era. But writing a CLAUDE.md correctly is far harder than it looks. The anti-patterns will surprise you. Here is where your existing expertise as a systems architect gives you a structural advantage that a prompt native engineer simply does not have. Classical information systems architecture follows a well-established pipeline. Requirements, engineering feeds to design specification, which feeds into implementation controls, which feeds into operational monitoring. Now overlay harness engineering on top of this framework. Behavioral specification maps directly to requirements engineering. You are specifying what the system must and must not do. The tool manifest and constraint boundary map to design specification. You are scoping the solution space. The agent topology maps to implementation controls. You are governing how components interact. And the observability interface maps to operational monitoring. You are maintaining runtime visibility and override capability. This is not a metaphor. It is a one-to-one structural correspondence. The engineers who struggle most with harness design are those who approach it as a new skill domain. The engineers who excel are those who recognize it as the application of a framework they already mastered. NIST's AI Risk Management Framework, published in 2023, independently arrived at exactly the same 4-phase structure for AI system governance. The discipline has deep roots. And the next section, we get hands-on with the code. So let's open the hood on a production CLAUDE.md file. A file that actually works in enterprise deployments has 5 mandatory sections, and they must appear in a specific order, because Claude reads top-down with priority weighting. Section 1 is the project context block, a concise declaration of what this codebase is, what domain it operates in, and what success looks like. This is not a marketing description. It is a constraint-setting preamble. Section 2 is behavioral guardrails, Explicit rules for what the agent must always do and must never do, stated as unambiguous imperatives. Sec 3 is tool permission scope, a whitelist of exactly which tools are authorized and, critically, under what conditions each tool may be invoked. Section 4 is the output format contract, specifying expected response structures, file naming conventions, and commit message formats. Section 5 is escalation triggers, the precise conditions under which the agent must stop, surface a decision to the human operator, and await explicit confirmation before proceeding. Notice that escalation triggers are listed last in the file, but are architecturally the most critical safety mechanism. A CLAUDE without escalation triggers is a system without a circuit breaker. And as any electrical engineer will tell you, a circuit without a breaker is not a system, it is a liability. Now let's look at what goes wrong. Now the anti-patterns, and these are more common than you might expect, even among senior engineers. Anti-pattern 1. Vague behavioral instructions. Writing "be careful with production data" is not a guardrail. It is a wish. The agent has no operational definition of careful. Replace it with never execute delete or drop statements without a preceding select that returns 0 rows. Measurably. Unambiguous. Anti-pattern 2. Permission sprawl without scope. Granting bash access without specifying permit commands is equivalent to giving a contractor master key to your building. Every permission must carry a scope qualifier. What commands, what conditions? Anti-pattern 3. Missing escalation conditions. If you do not explicitly define when the agent should stop and ask, it will not stop. Agents optimize for task completion. Completion bias is a documented failure mode in agentic systems. Anti-pattern 4. Missing failure mode declarations. What should the agent do when a tool call fails? Retrace silently? Surface the error? Abort the task? Silence on this question means the agent decides, and the agent will choose the path that keeps the task moving forward, which is often the wrong choice in a production system. Each of these 4 failures is a governance failure, not a model failure. The model does exactly what the harness permits. This brings us to a question that will reshape how you think about AI reliability. Who is actually responsible when an agent causes an outage? When your system moves beyond a single agent, CLAUDE.md alone is insufficient. You need AGENTS.md, and its job is fundamentally different. Where CLAUDE.md governs a single agent's behavior, AGENTS.md governs a network. It defines the topology. Which agent is the orchestrator, which agents are subagents, and critically, who has authority to write to shared state. Look at this structure. The orchestrator agent is declared with its delegation authority. It may spawn subagents, but may not directly modify the database. The researcher subagent has read-only tool access in a hard output format, structured JSON only, no prose. The implementer subagent has write access scope to non-production branches only. And the handoff protocol is explicit. Every agent handoff must include a structured context bundle, task state, completed actions, and a list of open assumptions the receiving agent must validate before proceeding. This handoff protocol is the equivalent of a formal interface contract in software architecture. Without it, you have not a multi-agent system, you have multiple agents independently hallucinating coherence. The discipline required to write a correct AGENTS.md will feel immediately familiar to anyone who has designed microservice AI contracts. And that parallel is exactly why this field belongs to systems architects, which is the core argument we will formalize in the next chapter. Here is the central tension in harness design, and it comes directly from classical control theory. Every constraint you add to an agent reduces its autonomy. But autonomy is what makes agentic systems valuable in the first place. Think of it as a dial. Turn it too far toward restriction. You get a brittle agent that escalates every minor decision to a human operator, creating approval fatigue and defeating the purpose of automation entirely. Turn it too far toward autonomy. You get a runaway agent that takes irreversible actions, deleting files, sending emails, committing to production, with no human awareness until the damage is done. The engineering challenge is calibration. And calibration requires a principled framework, not intuition. The framework I recommend is what I call the action risk matrix. Every potential agent action is classified on 2 axes. Reversibility. Can this action be undone? And blast radius. How many systems or users are affected if the action is wrong? High reversibility, low blast radius, full autonomous permission. Low reversibility, high blast radius, mandatory human confirmation gate. The intermediate zones are where your judgment as an architect is required, and where most harnesses are misconfigured. The uncomfortable reality is that the default setting of most AI coding tools sits dangerously close to the high autonomy end of this dial. The harness is the mechanism that pulls it back to a safe operating point. Calibration is only half the problem. Feedback is the other half. Constraints define what the agent is allowed to do. But constraints alone do not make a system safe. Observability does. A constrained agent that operates as a black box is still an operational liability. You need a feedback loop, and designing a loop correctly is as important as writing the constraints themselves. The feedback loop has three components. First, agent trace surfacing. Every significant decision the agent makes, every tool call invocation, every file it reads, every external API it queries, must be logged in a structured, queryable format, not as a log dump, but as a decision audit trail. Second, human-in-the-loop trigger design. HTTL triggers are not error handlers. They are preemptive decision gates that fire when the agent is about to cross a predefined risk threshold. The trigger fires before the action, not after. This is the difference between governance and incident response. Third, override interface architecture. When a human operator intervenes, the system must support three modes: pause and await instruction, roll back to a previous safe state, and full task abort with cleanup. If your harness does not support all three modes, you do not have an override interface, you have a kill switch, and kill switches destroy context. Design these three components correctly, and you have a system you can actually trust in production. Skip any one of them, and you are operating on faith. Let's look at the final piece of the control framework. And it comes from an unexpected source. The final piece of the control framework comes from Martin Fowler, and it is deceptively simple. Fowler's reversibility principle, originally articulated in the context of evolutionary architecture, states that you should prefer reversible decisions over irreversible ones, and when irreversible decisions are unavoidable, you should make them as late as possible with as much information as possible. Applied to agent action classification, this principle yields a concrete engineering rule. Before granting permission for any agent action in your harness, you must classify it as reversible, conditionally reversible, or irreversible. Reversible actions, reading a file, running a test suite, generating a draft, can be fully autonomous. Conditionally reversible actions, writing to a feature branch, calling an idempotent API, require scope constraints and trace logging. Irreversible actions, merging to main, sending an external notification, executing a financial transaction, require an explicit human confirmation gate with no exceptions. This three-tier classification is not optional in a production harness. It is the foundational safety contract. And here is the insight that connects everything we have covered in this chapter. The 5-layer harness stack, the CLAUDE.md and behavioral contract, the constraint calibration dial, the feedback loop design, and Fowler's reversibility classification are not independent techniques. They are one coherent system, an engineered control plane for autonomous software agents. In the next chapter, we will prove why this harness engineering a systems design discipline, and why that distinction has profound implications for who leads AI transformation in your organization. Here is the question experienced engineers ask when they first encounter harness engineering. Is this just configuration management with a new name? The answer is emphatically no, and the structural parallels to classical software engineering prove exactly why. Think about design by contract, Bertrand Meyer's foundational principle from the 1980s. A contract specifies preconditions, postconditions, and invariants. Now look at a CLAUDE.md file. It specifies behavioral preconditions, what the agent must assume about the environment. It specifies postconditions, what outputs are acceptable. And it specifies invariants, constraints that must never be violated regardless of the task. CLAUDE.md is not a prompt. It is an API contract for agent behavior. Similarly, your tool manifest, the list of tools you expose to an agent, is an interface definition. It declares capabilities, signatures, and access boundaries. This is identical to defining a Java interface or an OpenAI specification. The discipline is not new. The substrate has changed. But here is the critical insight most teams miss. Because they treat harness files as informal text, they lose all the rigor that interface design normally enforces. We are about to see exactly how much that costs. Let me make this even more concrete with a mapping table that should resonate with anyone who has written a software requirements specification. Traditional requirements engineering distinguishes between functional requirements, what the system does, and non-functional requirements or NFRs, which define quality attributes, performance, security, reliability. It also defines acceptance criteria, the testable conditions that confirm a requirement is met. Now apply this framework to a harness. Functional requirements in a harness are the explicit task capabilities. The agent shall be able to read and modify files within the designated workspace. Non-functional requirements become agent SLAs, behavioral constraints on tone, response latency targets, and output format standards. These are not optional style preferences. They are measurable quality attributes. Acceptance criteria become behavioral test cases. Given this input context, the agent must produce output within these observable boundaries. The IEEE 830 standard for software requirement specification does not need to be rewritten. It needs to be reapplied. Organizations that already have mature requirements engineering practices have a massive head start in harness engineering, but only if they recognize the mapping. Most do not. That recognition gap is where the competitive advantage lies right now. Now we arrive at the governance question, and this is where most teams currently fail. In mature software organizations, no significant architectural decision is made without an architecture decision record, or ADR. An ADR captures the context, the options considered, the decision made, and the consequences. It creates an auditable trail of why the system is the way it is. Harness files require identical governance. Consider what happens when a team modifies a CLAUDE.md to expand the agent's file access scope. Without governance, that change is invisible. Without version control, it cannot be rolled back. Without impact analysis, teams do not know which downstream workflows depend on the previous behavioral contract. And without regression testing of behavioral specifications, they cannot detect when a harness change silenced agent behavior in production. The process is clear. Every harness change follows a 4-stage governance flow. First, propose the change with documented rationale. This is your harness ADR. Second, perform behavioral impact analysis of all agent workflows consuming the harness. Third, run a behavioral regression suite, not unit tests of code, but tests of agent output boundaries. Fourth, promote to production with a versioned artifact tag. Martin Fowler has argued that infrastructure as code transformed operational reliability. Harness as code, governed with the same discipline, will do the same for agent reliability. In the next section, we will see who is actually capable of building this discipline and why the answer may surprise you. Let me be direct about something that the AI industry is reluctant to say clearly. Prompt engineering as a career specialty has a structural ceiling, and that ceiling is now visible. Here is why. Prompt engineering optimizes at the token level. It asks, given this model and this context window, what sequence of words produces the best single output? That is a valid skill, but it is a local optimization problem. Harness engineering asks a fundamentally different class of question. Given a distributed system of autonomous agents, how do I specify behavioral boundaries such that the emergent behavior of the system is reliable, auditable, and safe across all possible runtime states? That is a systems decomposition problem. It requires the ability to model failure modes before they occur, a skill called FMEA in traditional systems engineering, failure mode and effects analysis. It requires constraint modeling, identifying which system invariants must hold under adversarial conditions. It requires abstraction thinking, designing interfaces that hide implementation complexity while exposing necessary behavioral guarantees. These are not skills that emerge from writing prompts. They emerge from years of designing distributed systems, defining API boundaries, and debugging emergent failures in production. Senior architects do not need to unlearn anything. They need to recognize that their existing mental models are exactly what harness engineering demands. But here is the uncomfortable reversal, recognizing that is not automatic, and we will see who got there first. Let us examine a real-world anchor point. At one of the world's more open-source enterprise organizations published internal harness engineering documentation as part of their AI agent deployment program. What is remarkable about Red Hat's approach is not the technology, it is the organizational structure they built around it. They did not treat agent configuration as a developer-level concern. They elevated harness specification to an architectural governance artifact. They created standardized harness templates at the team level, what they call organizational harnesses, which define shared behavioral contracts across all agents operating within a business unit. Every team-level harness inherits from a corporate-level master harness that encodes enterprise-wide constraints, data handling policies, security boundaries, compliance requirements. This is a direct application of the Liskov substitution principle to agent specifications. A team harness must be substitutable within the corporate harness boundary without violating enterprise invariants. Red Hat also established harness review workflows integrated into their existing change advisory board process. The same governance body that approves infrastructure changes now reviews and approves harness changes. This is not an AI-native process. It is an enterprise IT governance process extended to a new ART class. That extension required systems architects who understood both domains. And that combination, enterprise governance fluency plus agent systems knowledge, is exactly the profile that is scarce and valuable right now. What competencies, exactly, does this profile require? The full map is next. Let me close this chapter by mapping the complete competency terrain for harness engineering practice. Think of this as the T-shaped engineer model extended in the agent systems domain. The vertical bar of depth runs through behavioral specification writing, the core craft skill. You must be able to write precise, unambiguous, testable behavioral contracts, not prose, not guidelines, contracts, but the horizontal bar of breadth is what separates a harness engineer from a documentation writer. 5 domains of breadth are required. Systems decomposition, the ability to decompose a complex business workflow into agent responsibilities with clean interface boundaries. Constraint modeling, identifying and formalizing the invariants that must hold across all runtime states. Observability design, specifying what the harness must make visible, logs, traces, behavioral assertions, so that agent systems are debuggable. Multi-agent topology design, understanding how harnesses compose when multiple agents collaborate, including the failure modes that emerge at the composition boundary. And finally, requirements engineering fluency, the ability to translate business intent into testable behavioral specifications. This is not a list of skills to acquire over months. Most senior architects already possess 4 of these 5. The 5th, behavioral specification writing as a formal discipline, is the new craft, and it is learnable. In the next chapter, we move from theory to production reality, how these principles manifest in actual enterprise deployments, what breaks first, and how leading organizations are solving it right now. The gap between understanding harness engineering and deploying it at scale turns out to be wider than most teams expect. Let's move from theory into production reality. Claude Code's CLAUDE.md is not a prompt file, it is a harness specification file. When Claude Code initializes a session, it executes a deterministic load sequence. It first reads the user-level CLAUDE.md from the home directory, then the project-level CLAUDE.md at the repository root, and finally any organizational policy overlays injected by the enterprise deployment layer. Each layer can extend but not override the constraints established above it. This is inheritance-based governance, the same architectural principle you find in RBAC systems and ISO 7701 access control hierarchies. The critical insight is that CLAUDE.md does not instruct the model what to say. It governs what the model is permitted to do, which tools it can invoke, which file paths it can modify, which external APIs it can reach, and under what conditions it must escalate to a human. That is the behavioral constraint pipeline, and it runs before a single token of your task description is processed. But here is what most practitioners miss entirely about this pipeline, and it changes how you design every CLAUDE.md file you will ever write. Now let's place Cursor's approach side by side with Claude Code, because the architectural differences reveal something profound about harness design philosophy. Cursor implements its harness through a rules configuration system, the TechCursor rules file, or the newer rules directory structure. On the surface, both tools accept structured natural language specifications that constrain agent behavior. But the architectural divergence is significant. Claude Code's harness is session-scoped and hierarchically merged at runtime. Cursor's rules are context-activated. Rules fire based on glob patterns matching the files currently in the editing context. This means Cursor implements a conditional harness. Different constraint sets activate depending on what the agent is looking at. That is more granular, but it introduces a new failure mode, rule conflict. When 2 activated rule sets contradict each other, Cursor's conflict resolution behavior is not formally specified. Claude Code's hierarchical merge is deterministic. Cursor's conditional activation is flexible, but requires the harness designer to reason about all possible rule activation states simultaneously. Neither approach is universally superior. They represent 2 different harness design philosophies, and choosing between them is now a systems architecture decision, not a tool preference. The question you must now ask: which failure mode is more dangerous in your production environment? Earlier in this lecture, we referenced the OpenAI Codex case study. 1 million lines of legacy code, autonomously navigated and refactored. Now I can show you what actually that possible, because it was not a clever prompt. The harness engineering design had 3 critical decisions. First, the specification structure. The task harness decomposed the codebase into bounded navigation zones, each with explicit entry points and prohibited modification areas. The agent could not free roam. Second, tool permission scope was surgically defined. The agent had read access to the full codebase but write access only to files matching a specific path pattern. It could analyze globally but act locally. Third, and this is the design decision most people never think about, the escalation protocol. The harness defined explicit conditions under which the agent must halt and surface a decision to a human engineer. Circular dependency detection. Test coverage dropped below threshold. and any modification touching a file flagged as a system boundary. These three harness decisions, zone specification, permission scope, escalation trigger, are what converted a 1 million-line problem from impossible to executable. This is harness engineering producing outcomes that prompt engineering cannot even conceptualize. And in the next section, we scale this pattern to enterprise level when harness engineering moves from individual developers into enterprise environments. A structural pattern emerges that every architect will immediately recognize: hierarchical inheritance with policy override controls. Think of it as a three-tier governance stack. At the base, individual developer harnesses define personal workflow preferences, preferred code style, local tool configurations, experimental feature flags. Above that, the team-level shared harness establishes the contract for collaborative work. Shared coding standards, branch naming conventions, test coverage minimums, and inter-service communication rules. At the top, the organizational policy harness enforces enterprise-wide constraints that cannot be overridden by any layer below: security policies, data handling rules, approved technology lists, audit logging requirements. This architecture is directly analogous to group policy object inheritance in Active Directory, or to the policy as code patterns you see in tools like OpenAI Policy Agent. What is new is that we are now applying this mature governance pattern to AI agent behavior at runtime. Every action the agent proposes must pass validation through the full stack, from individual preference up through team contract up through organizational mandate, before execution is permitted. Organizations that implement this correctly gain something remarkable: the ability to safely delegate complex autonomous tasks to AI agents without sacrificing governance. But wait, who is responsible when the stack has a gap? Nowhere is harness engineering more critical and more consequential than in regulated industries. Consider a financial services deploying an AI coding agent. GDPR and PCI DSS compliance requirements do not care whether the agent is intelligent. They impose strict obligations on any system that processes personal data, regardless of the mechanism. The harness must therefore encode compliance as a first-class constraint, not as a post-hoc guardrail. Let's walk through what this looks like concretely. PE detection must be a pre-execution hook. Before the agent writes any data to any destination, the harness intercepts and validates that no personally identifiable information crosses a data boundary without explicit authorization. Data residency constraints must be encoded as tool permission restrictions. The agent's file write and API call tools must geographic scope limitations hardwired into the harness, not requested in the prompt. Audit logging is not optional and not delegated to the model. The harness itself generates an immutable audit trail: every tool invocation, every file touched, every external call made. An escalation for ambiguous data classification must be automatic. The harness, not the model, decides when a human must review before proceeding. This transforms compliance from a legal checkbox into a harness design specification. The compliance team and the harness engineer must now work together. That is a new organizational requirement that most enterprises have not yet internalized. There is a final dimension to production harness engineering the industry has barely begun to address: harness specification regression testing. Consider the analogy to software development. When you change application code, you run a regression test suite to verify you have not broken existing behavior. The same discipline must apply to harness specifications. When you modify a CLAUDE.md file, a cursor configuration, or an organizational policy overlay, how do you know you had inadvertently altered the agent's behavioral boundaries? The answer is a behavioral test suite for harness specifications. You define a set of canonical agent act scenarios, some that the harness should permit, some that it should block, some that should trigger escalation, and you run this suite automatically whenever a harness file changes. This is continuous harness validation. The harness specification becomes a first-class artifact in your CI/CD pipeline, tested with the same rigor as your API code. Organizations that implement this close the final gap in production harness engineering. Without it, harness drift is inevitable. Your governance constraints silently degrade over time as teams make incremental edits to specification files with no regression safety net. This is not a nice-to-have. In regulated environments, it is the difference between demonstrable compliance and theoretical compliance. In the next section, we step at place everything we have built: the tools, the enterprise patterns, the testing discipline, into the full AI architecture landscape. Now we need to answer the architectural positioning question. Where exactly does harness engineering sit within the full AI system stack? This matters because without clear positioning, organizations will misassign harness responsibilities to the wrong team, the wrong layer, and the wrong tooling. Let me give you the definitive answer. At the bottom of the stack, you have the raw model API, the foundation layer. Above that sits the tool use and capability layer. This is where MCP protocol, the model context protocol standardized by Anthropic, operates. MCP defines how tools are registered, described, and invoked by models. Above the tool use layer sits the harness layer. This is where harness engineering lives. The harness does not define what tools exist. It defines what tools are permitted, in what context, with what constraints, and under what escalation conditions. Above the harness sits the orchestration layer, multi-agent frameworks, task routing, workflow engines. And above that, the application logic layer, the product features your users interact with. This positioning has a critical implication. Harness engineering is infrastructure, not application development. It is closer to network security policy than to feature code. Teams that treat CLAUDE.md as a developer convenience file are operating one abstraction layer too high. Harness is infrastructure. It must be owned, versioned, reviewed, and tested as infrastructure. And the discipline that governs this infrastructure has a name we have not yet formally introduced. With harness engineering properly positioned in the architecture stack, we can now map its relationships to the adjacent operational disciplines and identify where a new discipline is emerging. LLRNs the training and deployment lifecycle of machine learning models. LLMOps extends this to large language model deployment, prompt versioning, model evaluation, fine-tuning pipelines. DevOps governs the application software delivery lifecycle. These three disciplines exist today with established tooling, defined roles, and industry standard practices. But none of them owns the harness. Who versions and deploys the CLAUDE.md hierarchy? Who writes the harness regression test suite? Who is on call when a harness constraint unexpectedly blocks a production agent workflow at 2 in the morning? The answer today is nobody formally owns this. It falls between MLOps and DevOps in an ungoverned gap. What is emerging, and what the Martin Fowler, OpenAI, and Red Hat publication collectively point toward, even if they do not name it explicitly, is harness ops. The operational responsible for the harness layer's life cycle, including authoring standards, version control, regression tests and testing, response, and compliance reporting. This is not a future prediction. Organizations deploying AI agents at scale are already building these functions informally. The question is whether you will name it, staff it, and resource it deliberately, or let it grow as invisible technical debt. That is the choice that separates AI-native organizations from organizations that are merely AI-adjacent. And that brings us to the final chapter, where we synthesize everything into the harness engineering mental model and ask, what comes next? Let's step back and see the entire arc at once. From 2020-2022, the industry operated in the prompt engineering era, where a single well-crafted sentence was considered the unit of AI control. Developers competed over phrasing. The locus of control lived inside the human's head. Then the inflection hit. By 2022, models scaled past the threshold where raw text alone could not coordinate complex behavior. Context engineering emerged, RAG pipelines, memory systems, structured message payloads. Control moved from the sentence to the information architecture, but even that proved insufficient at scale. In 2025, with agents executing multi-step workflows across production systems, the industry crossed a second inflection. Harness engineering. Control is no longer about what you say or what you feed the model. It is about the system boundary you draw around it, the rules, roles, memory contracts, and tool permissions that define how an AI agent behaves as inside your architecture. 3 generations. 3 fundamentally different answers to the same question. Where does control live? The answer has moved outward, from prompt to context to harness. And understanding that trajectory is the foundation, everything you will build next. Now that we have the full historical frame, let me give you the 5 laws that govern harness engineering practice. 5 principles you can put on a card and use as a checklist on every AI integration you build. First, specify behavior, not instructions. Define what the agent must achieve and what it must never do, not how to phrase its thinking. Second, design for reversibility. Every harness component, system prompt, toolset, memory scope, must be replaceable without rewriting downstream consumers. Third, govern by layer. Persona rules live at the system level. Task rules live at the session level. Data rules live at the retrieval layer. Never mix governance layers. Fourth, test the harness, not the model. Your test suite must verify that behavioral constraints hold across model versions. If a new model passes your harness tests, it is deployable. Fifth, version the contract. A harness specification is a software artifact. It has a version, a changelog, and a deprecation policy, just like an API. These 5 principles are not opinions. They are the structural lessons extracted from every production failure we examined in the previous chapter. Miss any one of them, and your AI component will drift, degrade, or cause an incident you cannot explain. Carry these 5 rules into your next architecture review, and watch how they reframe every conversation. Here is the forward-looking question I want to leave you with, because every generation of AI control has ended the same way. An assumption that held true at one scale quietly breaks at the next. Harness engineering assumes that humans design the harness. A human architect writes the CLAUDE.md. A human team maintains the tool permission schema. A human engineer versions the behavioral contract. But what happens when the AI agent itself begins reading its own harness, evaluating its effectiveness, and proposing, or directly writing, revisions? We are already seeing early signals. Meta-agent architectures in research settings allow orchestrator agent to rewrite the system prompt of subordinate agents based on observed task performance. Self-modifying harness specifications are not a thought experiment anymore. They are a 2025 research prototype. This is Generation 4, and it represents a categorical shift. The locus of control does not just move outward, it moves upward, from human-authored specification to AI-generated governance. The engineering challenge of Generation 4 is not how to write a better harness. It is how to audit, constrain, and validate a harness that was written by a machine. The question is no longer what does my harness say? It is who, or what, wrote my harness, and can I trust the author? That question will define the next inflection. And the practitioners who think about it now will be the architects of what comes next. We have covered 3 generations of AI control, 5 laws of harness engineering, and the horizon of Generation 4. Now I want to close with 3 things you can do today, not next quarter, not after the next model release. First, audit your current AI tool configuration as a harness. Open your cursor rules file, your Claude project instructions, your Copilot workspace settings. Ask, does this define behavior and constraints at a system level? Or is it just a long prompt? If it is the latter, you have technical debt. Second, write minimal CLAUDE.md for your active project, even 10 lines. Define the project purpose, the coding conventions, the files the agent must never modify, and the test command it must run before committing. That is a harness. It is not perfect, but it is a starting point that can be versioned, reviewed, and improved. Third, identify which harness layer is missing in your team's AI workflow. Is it the persona layer? No constant role definition across team members? Is it the memory layer? Each session starts cold with no project context. Is it the tool governance layer? The agent can call any API with no permission boundary. Find the missing layer. Fix that first. The journey from prompt engineering to harness engineering is not a technology upgrade. It is a professional maturity upgrade, and it starts with the next file you open. Thank you for watching, and I will see you in the next series, where we go hands-on with harness templates across every major AI coding environment.